Gaussian distribution is important in statistics. It has been broadly used in science and engineering to represent real-valued random variables. A Gaussian distribution is a symmetry, bell-shaped probability distribution where most observations cluster around a central mean. The standard Gaussian distribution is centered at mean 0 with variance 1. The multivariate Gaussian distribution generalizes Gaussian distribution to n dimensions. The probability density function depends on a mean vector mu and a covariance matrix sigma, which together capture the center and the shape of the distribution. Let's consider a specific bivariate example. Our mean vector is 0 and the covariance matrix has a 5 and 7 on the diagonal with off-diagonal entries of 4. The off-diagonal entries tell us the two variables are positively correlated. Here's a 3D surface of this bivariate Gaussian. It peaks at the origin and smoothly decays in all directions, like a hill but tilted because of correlation between x1 and x2. Projecting onto each axis individually gives us marginal distributions. Both x1 and x2 follow 1D Gaussian curves, centered at 0 but with different spreads reflecting their different variances. Looking at the distribution from above, the level curves establish tilted ellipses. The tilted ellipse is a direct visual of the positive correlation between x1 and x2. A level set is the collection of all points sharing the same probability density. Setting the density equal to a constant C0 simplifies the exponent to a quadratic expression in x minus mu. To understand why the level set is an ellipsoid, we substitute the eigenvalue decomposition of the inverse covariance matrix. This rewrites the quadratic formula in terms of eigenvalues and eigenvectors. Inverting the eigenvalue decomposition flips each eigenvalue to its reciprocal. The quadratic formula becomes a sum of squared projections, each scaled by 1 over lambda I. The level set takes the form of a sum of squared projections divided by eigenvalues equal to a constant. This is precisely the equation of an ellipsoid, with the axis aligned to the eigenvectors and the length determined by the square roots of the eigenvalues. Back to the bivariate example, the level curve of the Gaussian is an ellipse whose axes are the eigenvectors u1 and u2 and whose semi-axis length depends on the eigenvalues lambda 1 and lambda 2. For the given covariance matrix, the two eigenvalues are approximately 1.88 and 10.12. The eigenvectors point in the directions of maximum and minimum spread of the distribution. It's easy to compute with NumPy. We pass a covariance matrix to NumPy's eigenvalue decomposition and get back both eigenvalues and eigenvectors in just a few lines. Here we plot the ellipse alongside the eigenvectors u1 and u2. The two perpendicular directions define the natural coordinate system of the distribution. Scaling each eigenvector by the square root of eigenvalue gives the actual semi-axis of the ellipse. The larger eigenvalue, lambda 2, scratches the ellipse further along u2. This is the complete geometric picture. The ellipse fully described by the eigenvalue decomposition of covariance matrix sigma. Shape, size, and orientation all come from the eigenvalue decomposition. Right now, let's verify this geometry by generating random samples. NumPy's multivariate normal function requires inputs such as a mean vector and the covariance matrix. With just 50 samples, we can already see the point clustering along the major axis of the ellipses. At 100 samples, the tilted elliptical shape becomes more obvious. With 200 samples, the distribution starts filling out the ellipse quite well. The elliptical shape and the empirical scatter are consistent. At 300 samples, the elliptical shape and the empirical scatter are even more consistent. With 1000 samples, the random samples almost perfectly traces the ellipse. This is a beautiful empirical confirmation of the geometry of eigenvalue decomposition. In the following, we change the covariance from positive 4 to negative 4. This means x1 and x2 are negatively correlated. The ellipse rotates in the opposite direction. With 100 random samples from this new distribution, we can already see the point spreading along the opposite diagonal, consistent with a flipped ellipse orientation. And with 1000 samples, the negative correlation is more remarkable. The random samples align with the ellipse, tilted from upper left to lower right. The eigenvalue decomposition of the covariance matrix completely determines the shape of the Gaussian. Here we see the ellipse for the positive covariance case, sigma with the off-diagonal 4. Placing both cases side by side for comparison, the two ellipses are almost symmetric, same eigenvalues, opposite eigenvector orientations. Thanks for watching this video. Feel free to reach out